Okay. What was that trouble? Only bread and everyone?
Yeah.
You know, it's fixed that. My late wife taught me this. What you do is when you first buy your bread, stick it in the freezer for about a week. Hills are coming. I have bread that sits out for 2 months, no mold at all. And it bugs me, it's bad stuff. The whole loaf is contaminated, even though you see a little bit of it. It's bugs have these little bread-like things that don't come with the surface. So if your bread is moldy at all, chuck it. But if you freeze it first, it kills the fungus. It's really cool. Doesn't cost you a penny to do that. Now, at my house, I have this refrigerator this wide and about this tall. And the freezing section is about this big. When you open my freezer, sometimes things fall out. And I cut it. So when bread comes, I have to, what I do is I do a couple slices in a Ziploc bags, I have to stick it in little places. That's another thing I'm gonna buy when I move. Big refrigerator. Okay, so I'm gonna mention. This should be big time review. Acid. What is an acid? An acid is a compound that disassociates a hydrogen ion. So number one, if it's got a hydrogen in the compound, it could be an acid. Only if it disassociates though. So not all hydrogens come off. If all of them come off, it's considered a strong acid. The acids we're going to be working in here are hydrochloric acid, HCl, and sulfuric acid. We're not going to be working with nitric acid at all. But these are the three strong acids you've probably run into in past classes. Okay, there's also something called a weak acid. And that's when only part of the hydrogens dissociate, not all of them. A good example of that is acetic acid or vinegar, aspirin, which we're going to be making in a little while. The fatty acids that come from various kinds of triglycerides, meat stuff. Okay, and then if no hydrogen ion dissociates, it's not an acid. There are three levels: strong, weak, and zero. Now, most of the carboxylic acids, the organic acids, are weak. Okay. And we use pH to measure how strong the acid is. The pH is something called the negative log of the hydrogen ion concentration. And log is a fancy word for exponent. So by definition, pH of 7 is considered neutral. Now, older homes have a problem because they have lead pipes. It's called a gooseneck. If your house is older than since 1950, you have probably a lead gooseneck in your house where the street water comes in and it connects to your household water. And the reason why it's lead is soft and you can bend it. So it doesn't matter if the angle isn't perfect coming in because you can bend it. Now, the problem is if your water coming into your house is slightly acidic, it will leach out the lead. So if you are living in an older home, whether it's a rental or you own it or your parents own it, have the water checked. You can buy a kit online. I think they're like $9 or something, not very expensive. Check your water. Flint, Michigan, that was their problem. Their water was below 7. That means it's acidic. I lived in Tacoma. My water there was acidic as well. My friend lived in an old house built in the 50s. I told him to get rid of that gooseneck. He didn't even know he had it. So he had a plumber come in and trench up to the street, put a new line in. And he thanked me really a lot because he said, unless I told him, he wouldn't have known. So lead pipes are bad. That's one of the reasons they speculate that the fall of Rome was blamed for. They had lead pipes. The peasants couldn't afford it. So their health was fine. In fact, peasant food is really good for you. A lot of fiber in it. And I eat a lot of peasant food. I go out of my way to make it. It's really fun to make. It also has lots of spices in it too, especially from Africa, like Moroccan food and Ethiopian food. It's really quite spicy and quite good. Also very healthy for you. Okay. Okay, so if the pH is less than 7, it's considered acidic. If it's greater than 7, it's considered alkaline. Alkaline is an old term from the Middle Ages during the alchemy time. Basic is a more modern term. And if pH is equal to 7, it's considered neutral. Now, whenever you talk about acids, you always think of the 3 types. Now, the interesting acids are the weak acids. There's a couple million of those. Strong acids, there are 7 in the world. Some of them are kind of not used very much. Who's ever watched the movie with Bryan Cranston and
Breaking Bad.
huh?
Breaking Bad. Breaking Bad.
Breaking Bad, yeah. Okay, who's watched that? Raise your hand. Okay, remember the scene with the bathtub?
Yes.
He was using hydrofluoric acid, HF, and it eats through lots of stuff. And that's why the tub came to the floor. I had a student back about 15 years ago. He worked for the Coast Guard. And he used to inspect container ships. And he had to wear a hazmat suit. Okay, and he had half the whole bit. He was doing his job, and all of a sudden he felt a weird feeling in his arm. He looked down, there was a hole in his hazmat suit, and HF was dripping from a container above, through the floor, onto his arm. And it ate through that hazmat material, which is extremely tough, and it burned a hole into his arm. He showed me the scar, it's a round scar. And he said he lost feeling in his arm for like 6 months. So HF is pretty wild stuff. But we're mostly going to be working with weak acids. Today we're working with something that has a pH of around 12. So it's very, very basic. Lye, sodium hydroxide. Okay, so let's. Okay, yeah.
Are these not on camera?
No. The problem is when I have notes on OneNote, and I say there's a way to print off the presentation, but it doesn't understand that paper is 8.5 wide. And it interprets the screen as being wider than that. So what happens, it cuts off the right side and moves it to the bottom. So it's really hard to follow. That's one of the big drawbacks of OneNote. Okay, there are different ways we're going to write a carboxylic acid. Carboxylic, easy for me to say, refers to the organic acid part, the COOH. That's made up of a carbonyl group here and an alcohol group here. Together, they're the carboxylic acid. Also, depending on what the R group is, it'll make the acid stronger or weaker. Now, if here's what it's looking for. When the acid gives off a hydrogen ion, what's left over is called the conjugate base. You might have learned this in 305. It depends on who taught it. But the conjugate base and the acid go together. What's not in the equation is the H plus. So the conjugate base plus the hydrogen ion that came off will yield the original acid. Now we're going to be synthesizing aspirin in a little while. Aspirin is an ester. It's also an acid at the same time. So that's why when your aspirin gets old, it smells like acetic acid. That's because HCl is given off when the things degrade. Here are some common acids. Probably the most common one you'll run into is acetic acid or vinegar. Some of the others, you run across it, but you may not know you did. For example, this school doesn't do the lab on esters and I did in the other schools, but it is a really cool lab. When you make an ester, they smell really fragrant. Really, they're really kind of cool to make. Okay, now sometimes acids have a really bad smell. Butyric acid is the first one I want to talk about. It's a 4-carbon acid, and it smells like cow dung. It's really bad stuff. But when you make an ester with methyl alcohol, you make oil of wintergreen. So you go from a cow patty smell to wintergreen. It's really a cool lab to do. There's one here. Anyway, a 5-carbon acid is called butyric acid. Okay, whenever you smell something rotting, smells bad, butyric acid. It's a 5-carbon acid. Okay, sometimes this is not cooperating. Sometimes when I want to move it, it writes. And other times when I write, it wants to move it. Let's do it this way.
Okay. I'm sure most of you have heard of the term fatty acid. And those are really long organic acids that are usually associated with cellular membranes, triglycerides, which is basically another term for fat. And they are like the start at carbon 16. So you're going to have 16 of these. And then the acid end. Now, the thing that makes fatty acids special is because of the long tail, they're very nonpolar. At the same time, they have a very polar end. And they always use fatty acids to make soap because of that property. Now, to be soap, you've got to have a polar and a nonpolar end to the molecule. If you do, it's like ivory soap. In fact, that's the soap we're making this week, is basically ivory soap. Now, you get to take it home, but don't use it for a while because the reaction is really slow. It's fast in the beginning, then it slows way down. And because we're making lye soap, you want to make sure all the lye is reacted away. So by tomorrow, your soap will be, or Tuesday people, tomorrow your soap will be nice and hard. So you can take it home anytime after this week, but don't use it until the semester's over. And I have moles, different kinds of mole hearts and stars and all kinds. Also, the citric oil you made, plus some other stuff I have, coloring and fragrance, you can make your soap to your own personality. Most students, that's their favorite lab, is the soap lab. So it should become. Okay. As you know by now, there's always two kinds of names for chemicals. There's a common name and then the official IUPAC name. So as far as the IUPAC name goes, it's the same as we've always been doing. It's in 3 parts. The ending is oic. Carbon backbone. And these are branches. Just like before. Okay, so we're going to identify our carbon backbone. And when we get into esters, there's going to be a secondary backbone like we had in Unit 2. So frequently you'll have 2 backbones. I always do yellow for the main one and pink for the secondary one. Okay, so you find the longest chain. Here we have 3 carbons. So that's a propane base, oic acid. So propanoic acid. Okay. Butanoic acid, 4 carbons. 1, 2, 3, 4. And in this case, it's got a branch. So this is, oh, and carbon number 1 is always the carbon that makes it an acid. Now, when you name this, notice that it didn't say 1 butanoic acid because the acid has to be carbon number 1, no exceptions. Now, you could have an acid that has 2 acid groups on it, though. And that's a dienoic acid. And we're going to find Thursday, we're going to have a 16-membered ring with a couple double bonds thrown in there. We're going to have a 20-membered ring with 6 double bonds thrown in. So there's a lot of things you're going to be learning about in here in this chapter. Okay, if it's resonant aromatic base, it's going to be based on benzoic acid. So that's always carbon number 1. Okay. Now, remember I always say that alcohols are the most polar chemicals we've studied so far. Acids are even more polar. So they're above acids in terms of intermolecular forces. So they like to hook up. They form something called dimers. That's where the two acid groups are attracted to one another. Also, they're very soluble in water. Water's soluble, water's polar, so the polar fatty acids mix well with the water. Okay, the fact is it has higher boiling points than alcohols, means that the intermolecular forces are stronger. So, alkane, like pentane, very, very insignificant IMF, just LDF only. Diethyl ether, we're increasing the polarity as we go down here. Notice the acids are at the bottom. Or this chart we've been using all semester is these are the acids up here. And depending on how large R is, they're very soluble in water because of the high polarity of the acid group. So if you put that carboxylic acid in pentane, it wouldn't dissolve because the pentane is totally nonpolar. Switch it to water, it dissolves, no problem at all. Like vinegar and water. When you buy vinegar, it's 5% acetic acid. And do you notice the difference between the acetic acid and the water in the bottle? No. So it totally dissolves in there. Not a problem at all. However, we start getting long chains, like carbon number 7 is always a key, that will then take over the polar part of the acid and make it not dissolve in water very easily. Okay, so this is something really important. You're going to get, this will be on the test for sure. And the next, in unit 4, there's the opposite of an acid, which is called an amine. So those two are always kind of taught together. Okay, so as far as an acid goes, go over here. If the pH is greater than 7, that means there's OH anion present. It will grab hold of the H of the acid part of the molecule and form water. Okay, and then it leaves the acid salt, the conjugate base of that acid. If you're in a acidic conditions where the pH is less than 7, nothing will happen. NR. Okay, so acids in an acidic solution don't do anything. Acids in an alkaline or basic solution come apart because the base will pull off that H from the acid. So you're left with the salt. Now this is how we're going to use it to make soap today. We're going to be creating a long carbon chain, an acidic group that has the H taken off. And that is called soap. Okay, it's also called a conjugate base. Yes, it's salt. Okay, Now, when you take off the H of the acid, its name changes. So we neutralize an acid. So what we're doing is we're putting sodium hydroxide with an acid. The OH of the base pulls off the H from the acid, it forms water. What's left over is the salt. Okay, so the name of the salt is the backbone plus ATE. So if we're taking hexanoic acid, 6-carbon acid, in a basic environment, that OH here two are going to form water. Now, what's left over is the sodium salt of the acid. So this is the now, the term salt is a generic term in chemistry. A salt is basically an ionic compound that's got a positive and a negative ions together. That's called a salt. Now, the one you're most commonly familiar with is table salt. That's sodium chloride. Sodium being positive, chloride being negative. But there are millions of salts in our environment and bodies. Millions. Okay, so if we start with hexanoic acid, throw in some lye or sodium hydroxide, we're going to make sodium hexa. We're going to make, where is it? Oh, right here. We're going to make sodium hexanate. Now, we're going to be talking about esters in a little while, and they're going to be OATE, O8. So there's nate and noate. So for now, it's just going to be ATE. So hex. So here's the backbone, 6 carbons. Base. We add those together, we make sodium hexanate. Okay, hexanate. If we're starting with a benzoic acid, what we end up with is benzoate. Now, sodium benzoate is used a lot in cooking, commercial cooking particularly. Does anyone know what it's used for? Has anyone, first of all, who's heard of sodium benzoate? Okay, all of 3 of you. It's used as a preservative frequently, and they use it a lot in baked goods and a lot of preservative. So look on your, I think it's even in Coke. Look on the food label whenever you buy anything that's not natural. Usually there's something called sodium benzoate, BHA, and BHT. All 3 of those are preservatives. They're not particularly good for you either. That's one of the downfalls of processed food. They have all these preservatives in it, so the shelf life is long, but then unfortunately, 1, they're expensive, and 2, they're not good for you. Now, do I eat junk food? Yes. Probably all of us in here have eaten junk food in our life. But I try to be aware of processed stuff as much as I can. Okay. Most of them, the acids are solid at room temperature. If you think of fat coming from beef, at room temperature, it's solid. It's greasy, but it's still solid. Same with pork fat. And chicken fat is mostly solid. It's a little in between. Okay. The sodium and potassium salts of fatty acids are called soap. Now, soap is an emulsifier. An emulsifier is a molecule with both a polar end that's supposed to be portion. So on your test 3, I'm going to show you a molecule. I'm going to ask you, is this an emulsifier? What you look for is a non-polar part and a polar part. If that molecule possesses both of those, it can act like an emulsifier or act like soap. Now, soap looks like this. Got a big, long, non-polar chain plus the acid end. Okay, so when you're washing dishes, I made artichokes yesterday, and Italian way of making artichokes, you use water and vegetable oil inside the artichoke. Well, it's a pain to clean up because you have all this oil in there. So I turn on the cold water, nothing happens, trying to clean this oily pot. I turn on the hot water. I mean, hot. I can't put my hand in it. It's a little better. As soon as I squirt in some dishwashing soap, it gets real foamy. And that's because the soap has that long tail that's nonpolar that sticks into the fat. The water is the polar end. So what happens is you can think of a soap or emulsifier as glue. And what it does is it glues nonpolar molecules to polar molecules. They're intermediate. And that's why you can stick soap in with your greasy food you're trying to clean up, and it'll grab hold of the grease, and it'll grab hold of the water, and that way you're able to wash it down the drain. Now, when you wash greasy stuff down the drain, do not use hot water. Anyone know why? Everyone uses hot water, right? What happens when the water cools down? Like about 8 feet down your pipe, it solidifies. That's how you get backups. If you start with cold water, it doesn't coat things. It just stays solid and kind of tumbles through your pipe. So now if you're using an emulsifier like soap, it helps that process. But if you're just washing fat down your drain and you use super hot water, eventually your system's going to back up. And it's really bad if you have a septic tank. Not good at all. Okay, do you have a question?
Are surfactants related to soaps?
Is what?
Surfactants?
Old fashioned?
Surfactants?
A surfactant?
Yeah.
Yes. Surfactant, gold, and emulsifier, all the same thing. Polar in, non-polar in. So equally interesting question, I can show you a molecule. Is this a surfactant? Look for polar and non-polar parts. It is, the answer yes. Now, it may not be a very good one, but it still will act as emulsifier or surfactant. Now, the word surfactant implies that the product will help the solid part of what you're trying to make non-waterproof. What happens is it clings to the, for example, Rain-X. Rain-X is a surfactant. You put it on your windshield and buff it off. What happens, the water beads off. It's like wax for your windows. So yeah, surfactants are used a lot. A way to kill mosquitoes is you put a surfactant on top of the water, and when the mosquitoes come to land on it to lay their eggs, the surface properties are no longer like water-like. What happens that the mosquitoes can't walk on the water anymore. Okay. Okay, now we found in Unit 2 that when we added an alcohol to a ketone or aldehyde, we formed a acetal or a ketal. If we added acid and an alcohol together, we form something called an ester. Okay, so an ester is made up of two parts. The alcohol part, which is this here, and this is the alcohol part from which it was made. Okay, to make an ester, you need acid plus alcohol. You get your ester. Now, here's where we're going to have a primary and a secondary backbone. The alcohol part, oops. And then we have the primary backbone. That's important to identify. So on the carbonyl side, the double bonded O is on the acid side, and the other one's alcohol side. Okay, the process of making an ester is called esterification. Biodiesel. Anyone? Okay, when I was in high school and in the Air Force for a while, they used to have these buses that ran around, particularly when I was in California, that were usually painted pink with flamingos on the side of the bus. And they would always say, this bus runs on biodiesel. To make biodiesel, it's very, very simple. You take fat, usually they got it from restaurants, and the restaurants would pay them to haul away the fat. Then you put in the fat, methyl alcohol, and a little bit of acid, and you cook it. And that's how you make biodiesel. It's just like regular diesel, only it's got an ester group in it. Only difference. Runs fine. It's messy as heck though. I work with a guy in Olympia who used to do that when he was younger. Anyway, that's how you make, and it's called transesterification. Okay, so esterification requires an acid and an alcohol. And there are three ways to make an ester. I had them lined out. Where did it go? Okay. Okay, method number one is you take the alcohol plus acid and you get your ester. That gives you the least yield. I'm going to cover the second one last. The third way to make an ester is with the alcohol plus the acid chloride. That maximizes the yield. And then there's an intermediate way is the alcohol plus the acid anhydride. Now, an anhydride looks like this. I always tell people an anhydride is like two esters together, and they share a common oxygen in the middle. So there's one, here's the other. So you need the acid anhydride, that makes the acid part of your ester, plus the alcohol. So the acid, instead of a pure carboxylic acid, you're using acid anhydride. And this gives you middle yield. So this is going to be a question on the test as well. Show me three ways to make this ester. Guaranteed. It's on every Unit 3 test I've ever made. Okay, so if this gives you the maximum yield, why would you use anything but that? Well, the problem with acid chlorides is they're very, very unstable. So the shelf life, when you buy it, is not going to last very long, and they're expensive. Why not then go with the alcohol and acid method? Well, the yield is very low. So the intermediate one, the anhydride, is what most people use to make an ester. That's what we're going to use when we make aspirin, is the anhydride of acetic acid. Okay, so let's look at an example here. Okay, if we're going to take method number 1, and we wanted to make a ethyl butyrate, or butanoate, what do we start with? We start with backbone, the primary backbone. That's the acid part. And then you always have a secondary, always a secondary backbone with esters. One starts with the acid, the other starts with the alcohol. In acidic conditions. Now, to name this guy, esters have 2 names that are put together. The first name is the alcohol name. Acid part. Okay, when we're looking at this ethyl butanoate, the acid part is next to the carbonyl group, the yellow, and it's 1, 2, 3, 4. 4 carbon acid. 1, 2, 3, 4. So we start with a 4 carbon acid, butanoic acid. Okay. If you look over here, there are 2 carbons. 2 carbon alcohol is ethanol. So if we start with butanoic acid and ethanol, we would get ethyl butanoate. Now there's butanate and butaoate, not the same. O8 is the ester part. Okay, if we take ethyl butanoate and take it apart, we're going to take ends up with our original alcohol plus the original acid. Okay, if we wanted to make propanoate, how will we do that? Well, what's this primary backbone? Draw the structure here. That would be C. That's methylpropanoate. Okay. So, backbone, boom, 3 carbons. That means we start with the 3 carbon acid, propanoic acid. Propanoic acid. Secondary backbone. One carbon alcohol, methanol. So propanoic acid plus methanol gives us methyl propanoate. Okay, so to weigh this, we can make it 3 different ways. We can make it with the simple acid and the simple alcohol, or we can make it from the acid chloride. So that's the acid chloride. And then we have the same alcohol. That's going to give us methyl propanoate. And the third way is we're going to need the anhydride of propanoic acid. So we need, now the anhydride is two acids coming together, forming the anhydride. So three carbon acid on either side, and it's linked together with the esters, a dual ester. Okay, so that's going to substitute so those are the three ways to make methyl propanoate. Alcohol plus acid, alcohol plus anhydride, alcohol plus the acid chloride. Acid chloride's the best. Plain old acid and the alcohol is the worst. Bless you. And the anhydride is the middle yield. Okay. You just need to practice finding the alcohol, finding the acid from which it's made. So you have a primary backbone, secondary backbone. Now, when you hydrolyze an ester, you end up with its original acid, original alcohol. Now, there's two ways to do that: acidic conditions and alkaline conditions. Acidic conditions, we yield the acid plus the alcohol. Like we start with ethyl acetate. Okay. Acetate comes from acetic acid, so it's 2-carbon acid. Ethyl comes from ethanol, 2-carbon alcohol. Ethyl benzoate starts with benzoic acid and ethanol. So when we hydrolyze that, we end up with the acids and the alcohol. Now, under alkaline conditions, the same thing happens, except for one big exception, is we form the acid salt. And that process under alkaline conditions is called saponification. Now, the name of your lab is saponification of seed oil. So we're going to be doing this reaction in lab this week. And this is going to end up being the soap. So fat is a triester. It's called triglyceride. You get your blood test and you do a lipid panel, it's called TG, triglyceride. Now you want to blood test, it'll give you a window of what's good and bad. You want to minimize the triglycerides, maximize the phospholipids, which is HDL, and you should ignore the LDL. Because the problem with ignoring the LDL is there are two kinds of LDLs. There's high density LDL and low density LDL. And the LDL test they do when your blood, they put them together. So LDLs are good and bad. So if you look at the triglyceride level in your blood test, they're not looking at phospholipids at all. They're just looking at triglycerides. And it's a better indicator of your bad LDL. So if your the good LDL. So if your triglycerides are low, then your good LDL will be low as well. If your triglycerides are high, that means your bad triglycerides are also bad. So people always look at TGs plus HDL. You want TGs low, HDL high. All right, so let's saponify this ester. Okay, it's a 1 carbon alcohol and a benzoic acid base. So we saponify it in an alkaline environment. We end up with the salt of the acid. So benzoic acid salt is sodium benzoate. Remember, the O8 also indicates a salt. And then the 1 carbon alcohol is just methyl alcohol or methanol. Okay? So if I ask you on the test, is this saponifiable? Number one, you look for the ester. Is there an ester present? If the answer is yes, then it's saponifiable. No ester, not saponifiable. Because the definition of saponification is you're taking apart an ester. So if there's no ester, there's nothing to saponify. Okay, guaranteed test question. Is this molecule saponifiable? Yeah. What is the ester part? It's this part, the yellow part. You need a carbonyl group and a double bonded O plus the O. So it's almost like OCO, only one of the O's is double bonded. Okay, so over here, OCO, one of them is double bonded, ester. Okay. Now, if they're both single bonded O's, it's an acetal or ketal. If one of them is double bonded, it's an ester. Okay. So the flow chart. If you start with carboxylic acid, add an alcohol, you end up with an ester. You add a base to carboxylic acid, you end up with the acid salt. Or if it's just in plain water, it disassociates. That means the H comes off. If you start with an ester, in an acidic environment, you can end up taking apart the original acid and the original alcohol. In a saponification, where you have a strong base, then you end up with a carboxylic salt plus the original alcohol. Now, these are the acids you're going to need to know. And I'm going to talk about these at length. I tell you, we have time on Thursday, probably on Tuesday. One, how to name them, and there's a delta nomenclature. Anyway, I'll talk in detail about this. Okay. Now, an ester requires an acid and an alcohol. We've only talked about organic acids to this point. You can also use inorganic acids like phosphoric acid. Phosphoric acid is found a lot in our bodies. Adenosine triphosphate, ATP, energy molecule. Adenosine diphosphate, energy molecule. So in the Krebs cycle, you enter into the electron transport cycle. Its function is to make ATP. And I'm going to, so that's a phosphate ester. There's all kinds of esters in organic polymers. For example, DNA. DNA is stuck together with esters. And there's 4 different base groups to define the DNA. And it's esters that put them together. So anyway, phosphoric acid esters are used a lot. Lipids are phosphoric lipid membranes. Again, phosphoric ester and phospholipids. Okay, now a phosphoric acid, phosphoric acid has 3 H's that can come off. So that means theoretically, you can make 3 esters from that one acid. And our body does that a lot. It uses 2 esters really a lot and 3 esters frequently. Okay, glucose 6-phosphate is the first step of glycolysis. What happens is carbon number 6, OH group, gets esterified with this. So this is that's the alcohol part. That's the acid part. And then what happens is carbon 6, carbon number 1 is phosphorylated in the next subsequent steps. So adenosine diphosphate is a phosphoric acid anhydride. Same with adenosine triphosphate. Those are anhydrides of phosphoric acid. And this is what ADP looks like. Okay, that's a ribose sugar. This is a nitrogen heterocyclic. It's called adenosine. And then here's the phosphoric acid anhydride. This would be adenosine triphosphate. What? No more slides? Okay. Are there any questions related to today? Now there's a Unit 3 flowchart. Okay, so we need to be a good idea to print that off. Okay, so we are going to